In this section or module, we're going to be looking at bonding and molecular structure. And the reason this is important is because the three-dimensional molecular structure of molecules is really important to how they function. In fact, if they don't have the right structure, they don't function properly. So this particular section can be divided into these three major sections of Lewis structures, molecular geometry, and molecular polarity. And it turns out that these are the order in which you want to understand these, because to get to the molecular polarity, that is to decide whether or not a molecule is polar, we'll understand that later, you first have to get the Lewis structure. And to get the molecular geometry, you first have to have the Lewis structure. And then to get the molecular polarity, you have to have the molecular geometry. So let's take a look at Lewis structures first. So for Lewis structures, we're looking at some major sections here. We're going to be looking at chemical bond formation, covalent bonding in Lewis structures, the octet rule, exceptions to the octet rule, formal charges, resonance, and then finally some practice. We'll probably divide this into two major lectures. So let's go ahead and get started, and we'll try and do these first three here. So let's look at chemical bond formation and Lewis electron dot symbols, where we're going to draw electron dot structures for atoms and ions. So when we look at chemical bond formation and Lewis dot symbols, there are basically three types of bonding that the book talks about. There's the covalent bond, which are shared valence electrons, ionic bonds, which are bonds between cation and anion due to charge attraction, and metallic bonding, where nuclei are in a sea of delocalized electrons. So the electrons are kind of holding the nuclei together. Now, what are valence electrons? And valence electrons are simply electrons in the outermost occupied shell. And we'll look at a little more about that in just a moment. So here, back to valence electrons. Valence electrons, for the main group elements, those are the two towers, those are going to be S and P electrons, and they're responsible for the chemical behavior of an element, or the atom of an element. So for instance, if we take a look at this electron configuration, 1s2, 2s2, 2p6, 3s2, 3p2, first of all, let's figure out what element this is. We add up the electrons, and you see there's 10, 14, and you look at your periodic table. The thing with 14 protons is silicon, so this is the electron configuration of silicon. So for silicon here, the 3s2 and the 3p2 are valence electrons. They are the outermost occupied shell. The fourth shell is not occupied, so it's not responsible for the behavior. The third one is. Now, what about the 1s2, the 2s2, and the 2p2, or 2p6, excuse me? Those are considered to be inner shell electrons, and they're not responsible for the chemical behavior. They're also called core electrons. So you have the core and the valence. The valence are responsible for chemical behavior. So if we take a look here at period 2 and 3 main group elements and their electron configurations, I'm going to go through this very quickly. Lithium here is 1s2, 2s2. Beryllium is 1s2, 2s2. And if you look at the number of valence electrons for lithium, it's 1. For beryllium, it's 2. And if we look at these other electron configurations for the period 2 elements, you'll notice that the number of valence electrons, here they are 1, 2, 3, 4, 5, 6, 7, 8. And the same goes for period 3. If you look at the valence electrons in period 3, there's 1 for sodium, 2 for magnesium, and so forth and so on. If you look at what group these are in, lithium is in group 1A, beryllium is in 2A, boron is in 3A, carbon is in 4A, nitrogen in 5A, oxygen in 6A, whoops, that's A, and then 7A, and then 8A. So if you want to know how many valence electrons are in the atom of an element, all you have to do is look at the group number. The group number tells you how many valence electrons. And that also tells you why these elements behave similarly. They have the same number of valence electrons. So lithium behaves like sodium because they both have 1 valence electron. Beryllium behaves like magnesium because they both have 2 valence electrons. Boron behaves like aluminum because they both have 3 valence electrons and so forth. So sometimes we find it useful to write electron dot symbols for these. And so the electron dot symbol, you draw the valence electrons as periods or dots. So again, the number of valence electrons is equal to the group number. And you normally draw the dots as singles per side before pairing. So you pretend the element has 4 sides, top, bottom, right, left, and you draw a dot on one side for the particular element. So for lithium, we're drawing a dot on the right-hand side, or you could draw it on the bottom, or you could draw it, oh, I did the bottom twice. So let me get rid of that one, and let's make that somehow different. So we're going to do this, if I can manage to do it. Well, that's not working, so we'll just leave it. You could have one on the top, and I'll cross that off, and one on the left. Doesn't matter which one of these you draw, they're all correct. So normally when you're drawing dots, and remember, this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. So normally when you're drawing these dots, you draw them as shown, where you draw 1 dot per side. And so carbon has 4 dots. And then when you get to 5 dots, you have to start pairing them up. And so nitrogen has a pair. It doesn't matter whether you put the pair on the bottom, top, left, or right, and so forth and so on. These are the dot symbols for the atoms. So let's take a quick look at a problem here. Valence electrons in the octet row. Give the periodic group number and number of valence electrons for each of the following atoms. So for oxygen, it's in group 6A. So what would the number of valence electrons be? 6. For boron, it's in group what? 3A. So it would have 3 valence electrons. For sodium, it's in group 1A, so it has 1 valence electron. Magnesium is in group 2A, so it has 2 valence electrons. Fluorine is in group 7A, so it has 7 valence electrons, and sulfur is in 6A, so it has 6 valence electrons. So there you go. All right. Next thing I want to show you very quickly, though, is ion formation with Lewis dot symbols. So let's look at ion formation using Lewis electron dot symbols. So we already know that group 1A atoms tend to form +1 cations. So here is what you draw for that. Here's a sodium with its 1 valence electron. And what happens is it turns into a sodium cation plus the valence electron being removed. So this is the ion formation using dot symbols. Likewise, if you had magnesium with 2 dots, it would become magnesium +2. And of course, for it to become a +2 charge, it has to lose 2 electrons. And so here they are. On the other hand, for anion formation, it's the opposite in that instead of releasing an electron, gas will have to gain electrons. So if you take a look at, say, fluorine, which turns into a fluoride ion, well, fluorine has 7 valence electrons. How does this become a fluoride ion? It gets an 8th electron. So we have to counter that by putting that there's an electron being added to the neutral atom of fluorine to give you a fluoride ion. And it's the same thing for an oxide ion, which has 6 valence electrons, and it becomes the oxide ion. Okay, so this shows you ion formation for these. Now, another interesting thing about these, if you take a look at the particular ion formed, sodium, it's 1s2, 2s2, 2p6. Magnesium, it's 1s2, 2s2, 2p6. And the fluoride is 1s2, 2s2, 2p6. And the oxide is 1s2, 2s2, 2p6. So this is the ion electron configuration. And you'll notice that for the ion, what is the most stable ion that forms? Well, it turns out it's the one where it forms an electron configuration like a noble gas. And when we look at valence electrons, it's got 8 valence electrons. When we look at the core electrons, it's got 2 core electrons. So for these elements that are in the second period, what happens to, or excuse me, the third period, and these that are in the second, so second and third, what do they end up doing? They end up losing electrons or gaining electrons until they have 8 valence electrons. And that's going to lead us to what's called the octet rule. So let's take a look at the octet rule, okay? Okay, so now we're going to be looking at covalent bonding and Lewis structures, and specifically we're going to focus on the octet rule. So the goal here is to apply the octet rule when drawing Lewis electron dot structures for simple molecules and polyatomic ions. We'll be coming back to this section and doing some more practice problems, but right now we're focusing on the octet rule. So if a compound or polyatomic ion has only nonmetals, bonding is covalent. So remember that shared valence electrons. The atom in compounds or polyatomic ions tend to share the valence electrons to get an octet. So here's the examples of these atoms achieving an octet of valence electrons, just like the ions do, but instead of being in an ionic compound or ions, these are in molecules where there are no ions. So here we have a fluorine atom and a fluorine atom, both having 7 valence electrons because they're in group 7A. And when they bond together, these 2 electrons are shared. And we see that because the electrons are directly between the 2 symbols of the elements. Now, this is called a single covalent bond. And normally it's not drawn as 2 dots between the 2 elemental symbols, but rather as a line. So a line represents 2 bonding electrons. So here, if we take a look at this structure here, you can easily see when I circle this that there are 8 valence electrons around this fluorine, and there are 8 valence electrons around this fluorine. So it turns out that those electrons in the middle are counted twice, so to speak, as far as how they're helping out atoms to be and have an octet. But you don't have to count them twice as the number of valence electrons. So when we count the valence electrons here, you got 7 plus 7, which is 14. And when you count these, you've got 14, 2, 4, 6, 8, 10, 12, 14. Here's another example where 2 oxygen atoms have 6 valence electrons each. So how do you get an octet around each oxygen with only 12? Well, it turns out that this is what happens. So here you have 4 shared valence electrons, which is considered to be a double bond. 2 electrons is 1 bond, 4 electrons is 2 bonds. So we draw it this way. So let's take a look at this oxygen here on the left. How does it have an octet? Well, it's got 2 non-bonding electrons, another 2 non-bonding electrons, 2 bonding electrons, and 2 bonding electrons. So it has a total of 8 on it. So the shared ones count for this oxygen and its octet. And these shared ones count for this oxygen and its octet. So this is a very nice way of sharing the electrons so that you get the octet. And so here, when they get the octet, they tend to be somewhat stable, like the noble gas in that period. Here's another example with 2 nitrogens that have 5 valence electrons each. So they get 10 total. And here you end up with a triple bond. And if we look at just the nitrogen on the left and count the valence electrons, it's 2, 4, 6, 8. Remember, each line counts as 2, so that's why I say 2, 4, 6, 8. And then if I cover up this nitrogen, how many valence electrons on that one? 2, 4, 6, 8. So we're obeying the octet rule, so to speak. Okay. Now, so what is the octet rule? Non-metal atoms tend to share electrons to get an octet. An octet tends to make them stable. Non-metal atoms tend to share electrons to get the same number of valence electrons as a noble gas in the same period. This is kind of the Tony's version of the octet rule. Really, you're trying to get the same number of valence electrons as the noble gas in your period. And when you get the same number of valence electrons as the noble gas in your period, you tend to become stable like the noble gas in that period. So what we're going to be looking at next are, let's see, we're going to be looking at exceptions to the octet rule. And the reason I have this here is it can show you exceptions to the octet rule, or how we might come to exceptions to the octet rule. Right here, this is just a list of the non-metal atoms of interest to us, the ones that are most likely going to be participating in covalent bonding. It shows their electron dot symbols, at least for periods 1 and 2. And I've left them off for periods 3, 4, and 5 because we know that the electron dot symbols are the same as you go down. So here, phosphorus would be 5. So 1, 2, 3, 4, and then 5. Normally you draw them as singles. So I'm going to cross that off, put a single there and a single there. Okay, so let's look at the number of bonds these things tend to make. So if you have one valence electron, you can only make one bond because you only have one electron to share. Helium, however, doesn't make bonds. So here, this is stable, having just 2 valence electrons. Now, I'm going to drop down here to neon. Neon has 8 valence electrons, and it's stable. If we drop down to argon, it's got 8 valence electrons, and it's stable. Krypton, 8, and it's stable. Xenon, 8, and it's pretty stable. So this is why we have the octet rule. More often than not, your atom in a period is going to most likely want to have 8 valence electrons. Okay, that's normally what happens. So that's why we have the octet rule. A clear exception to that is hydrogen, which makes 1 bond, and it'll end up being like helium. Now, boron with 3 valence electrons makes 3 bonds, but there's an exception, and it can make 4 bonds. Carbon normally makes 4 bonds because it has 4 valence electrons. There are no real exceptions for carbon until you get into some really fancy organic chemistry. Now, nitrogen has 3 singles and 1 pair. The pair can't really make a bond to another atom, but these 3 can, so normally this makes 3 bonds, but it does have exceptions of 2 or 4. Oxygen with only 2 singles makes 2 bonds normally, but it could make 1 or 3. And fluorine has 1 valence electron, so it normally makes 1 bond, covalent bond. And again, we've already done neon, 0. Phosphorus usually makes 3, but it also can make 5. Now, I haven't offered you any empirical evidence for this yet, but let's take into account here that it can make 5 bonds. 5 bonds times 2 electrons per bond is 10 electrons. So this phosphorus would have 10 electrons around it, and that's more than 8. So this is an exception to the octet rule. Sulfur normally makes 2 like oxygen, but it can also do 4 or 6. 6 is a clear exception to the octet rule. Chlorine is like fluorine, normally makes 1, but it could make 3 or 5. 5 is a clear exception. Argon, 0. Bromine is like chlorine, 1, 3, or 5. 5 is a clear exception. And iodine is 1, 3, 5, or 7. The 5 and 7 are clear exceptions to the octet rule. Xenon, interestingly enough, can also make 4 bonds, but it doesn't do it in very many compounds. So that's a covalent bond and Lewis structures and the number of bonds things normally like to make. So now let's take a look at exceptions to the octet rule. So exceptions to the octet rule. We want to recognize molecules and polyatomic ions that do not obey the octet rule. and draw reasonable Lewis electron dot structures for them. Right now, we're just going to be introduced to those that have exceptions to the octet rule. We'll practice drawing them later. So let's look at those that have exceptions to the octet rule. So again, this is my explanation of the octet rule. Main group elements tend to be more stable when they have the same number of valence electrons as the noble gas in the same period. So elements with less than an octet, we'll start off with boron. Boron has 3 valence electrons, and so therefore it can make 3 bonds. So here's it making 3 bonds with hydrogen. And the reason boron is okay with only 6 valence electrons is because it only has 3 to start with. So if each hydrogen brings in 1 valence electron, and it has 3 to start with, 3 plus 3 is 6. Here's another example. Aluminum is just like boron. It has 3 valence electrons. It's okay with 3 bonds, and it only has 6 valence electrons. Now, nitrogen has 5 valence electrons. There are times we can have less than an octet. For instance, in nitrogen monoxide, if we take a look here, we only have 9 valence electrons total. And so here, when you have an odd number of valence electrons, there's going to be an odd man out, so to speak, and one of your atoms will have less than an octet. And then, of course, there's everyone's favorite, hydrogen, which has 1 valence electron. And we look at an example. Imagine 2 hydrogen atoms come together with 1 electron each. This is what they're going to do. And so here, since it only has 1 valence electron, it can only form 1 bond. And so here, that's less than an octet. But in this case, we can justify it because it looks like helium. So this hydrogen here is thinking, aha, I look like helium. I look like a noble gas. And this hydrogen goes, huh, me too, because they're both sharing those 2 electrons. Here's some more exceptions to the octet rule. These are elements that have more than an octet, so they're called hypervalent atoms. These elements all are in period 3, 4, 5, 6, or 7. So any of those non-metals in 3, 4, 5, 6, or 7 can be hypervalent. That doesn't mean they will be. They can be. Usually not, though. Okay, so let's take a look at some examples here. Here's a sulfur atom with 2, 4, 6, 8, 10, 12 electrons around it. And that's an expanded octet, a hypervalent atom. However, if you look at each oxygen atom has 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. If we look at this I3 minus, you'll notice that the 2 terminal iodines have 8 valence electrons each, but the one in the middle has 10. So that's more than an octet. For this phosphate ion, you'll notice that the phosphorus has 10 valence electrons, whereas each oxygen has 8. And here for the xenon tetrafluoride, you'll notice that each fluorine has 8 valence electrons, but the xenon has 12. So these are exceptions to the octet rule. And eventually we want you to get to the place where you can actually draw these instead of just being shown them as examples. So this is back to the number of bonds atoms normally like to make. So hydrogen 1, boron 3 valence electrons, carbon 4 valence electrons, and so forth and so on. And you'll notice here that the bonds with asterisks next to them are ones that are expanded octets, hypervalent atoms. Okay, so those are exceptions to the octet rule. All right, so that's the end of the first half of this particular lecture for Lewis structures. We'll be looking at the second half for the next lecture. Thank you for listening.